Welcome and thank you for joining this webinar, The Architecture of Autonomy, Distributed Artificial Intelligence as a Native Capability of Future Wireless Networks, prepared by the Alpert Research Team. Wireless networks are entering an era where complexity, scale, and performance demands exceed what centralized control can manage. Distributed artificial intelligence enables networks to sense, learn, and act autonomously across devices, edges, and cores.
Now, there's another bottleneck here that the report highlights: communication overhead. It says that in large-scale distributed training, the communication between nodes can take up 80% of the total time.
That's right.
That feels like a huge contradiction.
That is the great irony and the central challenge of distributed intelligence. If everyone is talking to everyone else all the time, nobody is actually getting any work done.
So how do you fix that? How do you get the benefit of collaboration without the cost of constant communication? Even if we're sending mathematical gradients instead of raw data for a complex model, that update can still be pretty large. That's a problem for a small battery-powered sensor.
And that's where aggressive compression techniques come into play. The report focuses on two main ones: sparsification and quantization.
Sparsification, making something more sparse or empty.
In a typical neural network update, you might have millions of parameters. But it turns out that for any given update, most of those changes are tiny and insignificant. Sparsification is a technique that says, let's only send the most important changes.
So you find the top 10% of the gradient values that have the biggest impact, and you just send those.
Exactly. You set all the other tiny values to 0, you're sending a sparse update. It dramatically reduces the size, and it turns out that the models are robust enough that they learn just fine without all that minor detail.
In quantization.
Quantization is about reducing precision. A standard number in a computer is a 32-bit floating point number, which can represent a huge range of decimal places, very precise. But for training an AI model, do you really need to know that a weight should be 0.456789123? Or is 0.46 good enough?
It's introducing a bit of fuzziness to save space.
By quantizing those 32-bit numbers down to 8-bit integers, or even 4-bit, you can reduce the data volume of the model update by 90% or more. It's a complete game changer for massive IoT. Let's talk about the big bottleneck here. We started by talking about the cloud bottleneck, but it seems like distributed systems have their own version of this problem.
They do.
The report cites a pretty shocking statistic that communication overhead can account for up to 80% of the total execution time in large-scale distributed AI training.
That is the communication crisis. We've solved the problem of moving the computation out, but now the nerves connecting the different parts of the brain are clogged. If the agents spend all their time talking to each other, here are my model gradients, here is my bid, did you get my last message, can you acknowledge receipt? They get no actual work done. You've distributed the thinking, but you've created a new bottleneck in the talking.
So what's the solution? You can't just tell them to stop talking to each other.
The solution is to talk smarter, not more. The main technique here is called gradient compression. It's basically realizing that you don't need to say every single word perfectly to be understood. The report details a few key techniques. One is sparsification, where an agent only sends the most important updates. If a parameter in its local model only changed by a tiny amount, it just doesn't send that update. It only sends the big changes.
And the other one is quantization.
Quantization is about lowering the precision of the numbers you do send. An AI model is just a big list of numbers. Instead of sending a number to 16 decimal places of precision, you round it off and send it to just 4. That neural networks are surprisingly resilient to this kind of noise. The report says these techniques combined can reduce the data volume of these updates by 90% or even more. The report mentioned something even wilder, a wireless twist on this called over-the-air computation.
It completely flips a core concept on its head: interference. For the entire history of radio, if two signals collide in the air, we've called that interference. We spend billions on engineering to try and prevent it.
Right, you don't want your call to get mixed up with someone else's.
But over-the-air computation asks a radical question. What if we could use that interference as a feature? What if we could make the signals mix in a useful way? Okay, think of the hikers again. Instead of each hiker radioing in their step one by one, what if they could all just shout their step at the exact same time?
It would just be a wall of noise, right?
But with over-the-air computation, each device carefully encodes its numerical update, its gradient into the phase and amplitude of its radio signal. They're designed so that when all those signals physically superimpose in the air, when they all add together at the receiver's antenna, the resulting waveform's value is mathematically equal to to the sum of all the individual values.
The physics of the waves colliding does the math for you.
The atmosphere becomes your analog computer. The receiver just has to measure the property of that one combined signal to get the aggregated result instantly. It's incredibly efficient because you eliminate the need for each of the millions of devices to get its own individual time slot to transmit. It's a true native AI concept. The report is very upfront about the unique challenges that wireless imposes.
Let's talk about the biggest one for me, which is heterogeneity. In one of these federated learning networks, you're going to have the brand new smartphone, and you're also going to have a 5-year-old smart thermostat with a tiny processor and a weak battery. If they're all supposed to be collaborating, doesn't the slowest device, the thermostat, hold everyone else back?
That is the classic straggler problem. If your server has a synchronous protocol where it has to wait for every single device to check in before it calculates the next update, then yes, your billion-dollar network will run at the speed of the cheapest thermostat. It's completely inefficient. The much smarter solution is to use asynchronous updates, meaning the server doesn't wait, it moves ahead, it has a time window, and it processes all the updates that arrive within that window. The fast devices report in, the server updates the global model, and the process continues.
What happens when the slow thermostat finally sends its update? It's based on an old version of the model.
It's a stale update. So the server accepts it, but it applies a penalty. It mathematically downweights the stale update.
So the fast devices lead the way, and the slow devices contribute what they can when they can without slowing everyone else down.
The challenges and the risks.
If you don't optimize that with things like gradient compression, the whole system grinds to a halt. The report has this metric, MFU, or model FLOP's utilization. It's basically a measure of how hard your expensive AI chips are actually working versus how much time they spend waiting for data. They show that as you scale up a distributed system, if communication isn't optimized, the MFU can drop from a healthy 47% all the way down to 4%.
So you have millions of dollars of GPU power sitting idle 96% of the time because they're just waiting for data. Another challenge mentioned is simply the reality of wireless constraints. This isn't a clean, reliable fiber optic cable in a data center.
Not at all. Devices drop off the network all the time, signals get weak. We call this intermittency. Your training process has to be robust enough to handle nodes disappearing and reappearing. And then there's a really tricky data science problem called non-ID data. Non-independent and identically distributed. It just means the data isn't the same everywhere. The real world is not uniform. The problem is, if you try to train a single global driving model by averaging the updates from both of those places without accounting for that difference, you get a model that is mediocre at both.
So the distributed agents need to know that their local reality might be unique and not representative of the whole.
You need more advanced techniques, like personalization layers in the model. The global model gives you the basic physics, but the local layer adapts to specific conditions. Distributed artificial intelligence is central to the evolution of 5G Advanced and 6G, redefining how wireless networks are designed, operated, and trusted in the autonomous era.
It really is the future of the field.
And if you are interested in gaining a deeper understanding of the transformative power of wireless technology, the Alpert Research Team runs webinars where they explore these cutting-edge wireless innovations, their applications, and their implications. We encourage you to click the links below to learn more.
It's well worth your time if this topic is interesting to you.
Thanks for listening. We'll see you next time.